Greetings. My name is Yogendra Joshi. I am a program manager in the Microsystems Technology Office. And I would like to talk to you today about controlling thermal transport, which will enable revolutionary capabilities in future microsystems. As part of my background, I have been at DARPA since July 2022. And prior to that, I was on the Faculty of Mechanical Engineering at the Georgia Institute of Technology. And my undergraduate and graduate background is in mechanical engineering. Currently, I manage programs in the area of thermal management. Two of my programs include Mini-THMS 3D. Mini-THMS 3D is looking at thermal management technologies to enable stacking of multiple high-power tiers of multiple materials, not just silicon, but perhaps materials such as gallium nitride, each tier generating in excess of a kilowatt of power. There are, of course, multiple challenges in stacking high-power three-dimensional chips in a three-dimensional topology. Of course, if this could be done, this will have revolutionary impact on the performance of future microsystems. The key challenges, of course, make this difficult so that the temperatures currently in the interior of the stack become unacceptably high. The program is addressing two major challenges. One, heat spreading and transport within the stack. And the second challenge of taking the heat away from the edges of the stack to a remote heat exchanger and then rejecting it to the ambient air environment, all in a very compact form factor. Within the stack, of course, there are multiple challenges. First, since the thickness of the tier is relatively thin, the spreading of heat from hot spots, which are becoming increasingly more prevalent, very difficult. So the heat spreading problem is just one of the key challenges. Of course, the other challenge within the stack results because we are co-locating multiple functionalities within individual tiers, including logic, memory, and other types of functionalities, each requiring maximum temperatures to be restricted below a certain value. And when these functionalities are located in close proximity to each other, there is a tendency for the heat to be transported from one to the other, which requires very strong thermal isolation. That's another component of the program. And then, of course, as we start stacking multiple tiers, the heat removal, which is traditionally done just from the top and bottom of a stack, is not feasible because it can then heat up the interior tiers as well. So we need to have the ability to remove the heat individually from the tiers as we stack a multiplicity of them. All of that happens inside the stack. And then, of course, we have to look at heat transport from the edges of the stack through a very low thermal resistance pathway to a remote heat sink, which then rejects the heat ultimately to the ambient air environment, again, in form factors that are significantly smaller than what is possible today. All of these challenges are being addressed as part of Mini-THMS 3D. The Thermonet program is a microelectronics exploration, which is looking at multi-scale thermal modeling approaches and methodologies to look at modeling of individual transistors. And these are emerging transistor architectures such as FinFET and gate-all-around, where individual material layer thicknesses are on the order of just a few nanometers. And the reliability predictions for these types of new architectures require accurate predictions of where the heat's being generated within these new architectures is a challenge at the smallest scales. But at the same time, we also want to be able to analyze the thermal characteristics at the circuit scale, which includes perhaps several 100,000 transistors, such as perhaps a phase lock loop. This seamless modeling from individual transistors to several 100,000 transistors is extremely challenging, particularly if it has to be done fast and with high accuracy. And that is what the Thermonet program is targeting. Collectively, these programs will enable new thermal technologies that will then be utilized in future emerging high-performance microsystems. My programs are addressing emerging needs for microsystems. In particular, we're seeing where thermal designs and thermal technologies looked at really steady state or static conditions. That is no longer the case in microsystems, which are being deployed increasingly in operational envelopes and environments which are changing in time, many times very rapidly. And being able to address and control thermal transport under these types of conditions allows then for us to have microsystems that are significantly more capable than the ones that are there today. And that's the sort of common theme in my program. And I'll discuss some of the areas of interest that fall within these overall guidelines. I take three examples here. The first one is about harsh environments, and these could be temperatures that are potentially 1,000 degrees C or higher, or on the low side, perhaps minus 270 degrees C or even lower. Again, some of these applications have been around for some time, such as re-entry vehicles, etc., which encounter very high temperatures, but typically for relatively short durations. What about very high temperatures in high-speed flight that may last a few hours? And again, the thermal management challenges include not only protecting the microsystems from such prolonged exposures to the harsh environments, but also being able to reject the heat that's being generated within the microsystems. These seemingly conflicting requirements have to be simultaneously met. In this type of an application scenario where one could potentially handle both of these capabilities simultaneously, one could potentially achieve, let's say, a flight from Washington, D.C. to Tokyo in 2 hours, which would be truly revolutionary. That's at the high end of temperatures. At low temperatures, again, there are many challenges, such as, for example, that are faced by spacecraft in emerging technologies such as low Earth orbit type applications, where the microsystems may face very high temperatures during sun exposure, solar exposure, and then very low temperatures when exposed to deep space environments. How does one simultaneously handle these transient and dynamic environments? So handling these types of harsh environments is certainly a key area of interest. Another area of interest is looking at computing systems beyond the current generation of high-performance computers. Many have argued that quantum computing potentially offers such an opportunity in future. However, getting quantum systems that can potentially meet and beat the performance of modern computers requires having these qubits. Again, I'm talking about superconducting qubits here. There are other topologies that might potentially become important in quantum applications as well. But considering superconducting qubits, one potentially needs thousands to possibly millions of these qubits in order to get superiority in computing compared to the modern computing architectures. This, of course, requires maintaining these qubits at temperatures that are well below 10 or on the order of 10 millikelvins. And the sort of most common way of doing that is through the use of dilution refrigerators, which utilizes the helium-3 to helium-4 transition for evaporative cooling to get down to those temperatures. However, the cooling power available at 10 millikelvin is only on the order of hundreds of microwatts. As we scale up the number of qubits, the heat leaks as well as the heat generation contributions scale up well beyond the available cooling power. And so clearly key advances in packaging architectures and materials are needed, and innovations that would enable that progress certainly would be key to getting to those types of scalable superconducting qubit-based machines. This topic is of interest to us, and we are actually planning a workshop on this later this year. And certainly, if you have transformative ideas in this space, please do consider attending our workshop. A third area is looking at thermal radiation characteristics. And again, current approaches for changing radiative properties look at a single switch or a relatively narrow spectral range where a property changes its values. And there are examples in the literature used, for example, for spacecraft thermal control, camouflage applications, as well as for radiative cooling type applications. These utilize approaches such as using microlouvers or spacecraft thermal control using carbon fiber polymer structures whose radiative properties at narrow wavelengths can be altered. And for camouflage applications, changing properties in the visible spectrum as well as parts of the infrared spectrum have been demonstrated. However, changing these in an on-demand fashion, utilizing active control approaches for changing these properties is an area that remains open, and we have an interest in that area as well, and are planning a workshop on this topic in early 2025. So, what are we looking for in terms of help from the community? We are interested in adaptive control of thermal transport and thermal properties. This will enable whole new generations of microsystems and will unleash new capabilities for these types of systems. And the challenges are particularly coming because of the changes in the operational environments as well as the operational characteristics of these types of microsystems. We are, of course, looking for transformative ideas, not incremental advances in these areas. If you have thoughts and new ideas on any of these topics, certainly would be interested in hearing about those, and I'd be receptive to getting just a few slides, perhaps 5 slides or less. And what we would like to be able to see there is, first of all, what is it that you would like to do that just cannot be done today? Why can it not be done today? And then why you think your approach will be successful. So we look forward to hearing further from you on any of these topics. Thank you.